Okay, so let's start this sixth iRobot. This is the fifth iRobot in EPIA, and this year we had a large number of submissions in previous occurrence of iRobot. And on this session we'll have 4 papers. The first one will be presented by Francisco Campos and is entitled Loop Closure Detection with the Holistic Image Feature. Okay, you'll have about 20-25 minutes for the presentation plus 5 to 10 minutes for questions. Okay.
Hello, good afternoon. I'm presenting a work entitled Loop Closure Detection with a Holistic Image Feature, which was developed by myself with the collaboration with the professors Luís Correia and João Calado. This work is concerned with the loop closure detection, so I'll start by defining what this problem is and why it is important. Imagine that we have a robot traveling a path in a given environment and describing this trajectory in the dotted line. And if we were to use only odometry to estimate the robot trajectory, we may end up with an estimated trajectory like the one in the red line. There is a gross error there, which is due to the well-known accumulation of errors in odometry. On the other hand, if we're looking for loop closure events, we may notice that when we arrive at this place, we are in a place which is very similar to a past one, and if we actually conclude that those places are the same, we are signaling a loop closure event. If we can do this successfully, then we can correct the previously estimated trajectory. I mean, we can impose that constraint and arrive at this new estimated trajectory. So we will correct the metric map, and also we'll have more correct topological map. By this I mean that in this map we have an unconnected line which does not correspond to reality, and by using this map, if we wanted to go from this place to this place, for instance, we would have to go this way around because we don't know there is a connection there. Of course, if we have a topologically correct map, we can do the shorter path. In this work, we are looking for loop closure events by using image data. And for this purpose, we proposed a new image feature, which we called LBP-GIST, which combines 2 well-known methods. One is the local binary patterns, which is used to describe textures in an image, and has been successful in many different tasks, such as face recognition, background subtraction, texture classification. And it is very attractive because it provides good descriptive power, in spite being very fast to compute. On the other hand, we use some ideas from another feature, GIST. GIST also uses textures, but it wants to extract the global content in an image. Specifically, it tries to extract the spatial structure in the image, and for that purpose, it divides the image plane in a fixed grid and computes the texture filter responses in each block of that grid. So the presentation will be organized as follows. I will start by giving some background concepts from local binary patterns. I will then move on to define the proposed feature, LBP GIST. I will also show an hashing scheme we use to achieve fast image retrieval, and conclude the presentation with the results and conclusions. So in the original LBP operator, the first step is to convert an intensity image to a labeled image, where each pixel is assigned a label that describes the texture pattern around it. In order to do this, we extract a 3x3 neighborhood around that pixel, and we compare the border pixels. We compare the border. Sorry. We compare the border pixels with the center pixel by using a threshold function. Through this function, an intensity level above the center pixel will be assigned a 1, while a lower level will be assigned a 0. In this way, we arrive at a binary string if we read the bits that way. And we can convert that binary string to a decimal number, and this will be the label for that pixel. The final step will be to compute an histogram of the labeled image, and this histogram can be used as a descriptor of the image content. Later, the authors of the LBP operator proposed a multi-scale operator which allows us to extract textures that extend over larger neighborhoods. This operator is parameterized by 2 parameters, a radio and the number of sampling points. Here we have some examples, all with 8 samples and different radius. So the radius is the radius of the circumference where the sampling points are distributed, and the p parameter is the number of sampling points we will read around that circumference. In order to analyze the properties of different patterns, the authors of LBP defined a uniformity measure, which is the number of transitions from 0 to 1 or 1 to 0 that we find when going along the sampling points. So we have patterns such as these, which have uniformity 0. Here, uniformity 2, we have one transaction and a second transition, and here some examples of a uniformity measure for patterns. The authors found that the patterns having uniformity up to 2 are the most frequent in natural images, and they often define a mapping where patterns having uniformity measure above 2 are assigned to the same histogram bin, and in this way they will arrive at a smaller descriptor. Also, it is possible to obtain some rotational invariance with the LBP. Here are some examples of some patterns that can be achieved by a simple rotation, and it is possible to define a mapping where we achieve rotational invariance by assigning all these patterns to the same bin, and in this way descriptor can be reduced to length 10. So let me define now the proposed feature, LBP GIST. As I mentioned, it uses LBP with some parameterization and some modification. First, the modification we use is on the threshold function. we noticed that when we apply LBP to image areas which are close to flat areas like this one, there will be a lot of noise in the labeled image. This is because even small intensity differences will give rise to different LBP patterns. So in order to eliminate that noise, we defined another threshold function where we don't strictly compare the intensity values of the border and center pixel, but we add some constant term and also a factor term that multiplies the center pixel value. Let's see now the parameterization we used on LBP, for LBP GIST. We used the multiscale operator with 8 samples and radius 9. In order to have better discriminativity, we used a non-rotational invariant mapping. And also we included patterns with uniformity up to 4. So in the end, we can conclude that the length of an histogram in LBP GIST will be 199, because we have, let's see, we have two uniform patterns, 56 uniformity 2 patterns and 140 uniformity 4 patterns. All patterns with uniformity above that are assigned to the same bin. In LBP GIST, we also use concepts from GIST. That is, we want to extract some spatial content in the image, and for that purpose, we apply a fixed partition of 5 blocks. We have these 3 horizontal blocks which are non-overlapping, and then we also define 2 overlapping blocks defined by those blue lines. So in order to extract LBP GIST, we compute a labeled image for each of those blocks, and we computed the corresponding histograms. So an LBP GIST descriptor will be a set of those 5 histograms, and will have a length of 995. In order to conclude about loop closure, we must have a way of comparing LBP GIST descriptors. Let's see how we define a similarity measure between them. Imagine that we have a test image and an image from a database of past places that the robot has visited, and we want to compare them. For each one, we have the corresponding LBP GIST descriptor, which is a set of 5 histograms, and we compute a distance between corresponding histograms. In this way, we will arrive at 5 distances. These distances are chi-square, which is what's usually used with LBP histograms. And we convert this measure to a similarity measure through an exponential function. To arrive at a global similarity measure, we sum up the partial similarities, which are weighted by a weight, which allows us to give more importance to some areas of the image than others. For instance, in this case, the upper area, which is the sky, doesn't seem very informative. So it would be assigned a lower weight. In our experiments, we concluded that a value for the similarity, a good value to use as a threshold to signal a loop closure, would be 0.7, which is what we will later use. In order to achieve fast comparison, we use a hashing scheme. This allows us not to compare every image in the database to the test image. The hashing scheme will provide us with a short image list, which will be used by this comparison block to select only some of those descriptors. For this purpose, we use an hashing method in the family of locality-sensitive hashing, where descriptors are processed by a hashing function that will put image indexes into an hash table. These hash functions should be so that similar descriptors are assigned to the same bucket, while a different descriptor from those should be assigned to a different bucket. There are some theoretical guarantees that the locality-sensitive hashing scheme should offer. That is, the probability of two similar descriptors being assigned the same bucket should be over P1, and the opposite lower than P2. An hashing scheme can be further improved by the concept of sketches, where we combine a number of hash functions. For instance, if we use two hash functions, the hash table would be bidimensional, with the first hash function indexing the first dimension and the second dimension. In this way, we can increase the gap between the probability of assigning the same bucket to similar and dissimilar images, because the probability of collisions will be raised to t. These probabilities will be lower, so in order to increase the probability of collisions, we can also use several hash functions in parallel, which is what we will do. The particular hashing scheme we use is called winner-take-all hashing, where the probability of collisions is not related to an Euclidean distance between descriptors, but rather to a rank order similarity. What does this mean? It means that two descriptors are similar not because the absolute value of their elements is close, but the ordering of the elements is similar. For instance, these two descriptors, I could look at this value and see if it's close to that value, but that's not the kind of similarity we are measuring. This kind of similarity gives importance, for instance, to the fact that this element is greater than this one, which in turn is greater than that one. That relation applies to that descriptor too, so this relation it contributes to a higher similarity between those descriptors. Let's see how we define a hash function to winner-take-all hashing. The hash functions here are based on k-order permutations, which means that we obtain these by taking the indexes of a descriptor and computing a full-length permutation, and a k-order permutation will be just a vector of the first k elements. How we apply this hash function? We take the permutation, apply it to a descriptor. So, for instance, in this case, the first element in the permutation is 26. We pick that value, and so on. And according to winner-take-all hashing, what we will do next is look for the maximum of this vector, and the output of the hash function will be the index of the maximum. So here, this is the maximum, and the output of the hash function will be the index, so 2. We proposed some modifications to this hashing scheme. What we will do is not retrieve all the images where collisions are found, but rather see the number of collisions as a similarity measure, which allows us to have better efficiency in the selection of images to process. So we define a similarity measure as the number of collisions we find, and we modified that similarity measure according to a scheme which is often used in the bag of words model, which is the TF-IDF weighting of words in the bag of words model. Here, only the IDF term makes sense to use. It's the inverse document frequency, and this weight is computed as the total number of images that were processed over the number of images in that bucket. We compute the logarithm of this ratio, and that will be a weight to be applied to collisions found in that bucket. So this will give lower weights to buckets where lots of images were inserted, which means that they are not so relevant. Also, having this similarity measure defined, we use another condition to select images, which is to establish a threshold relation between the image getting the highest score and the other one. So we only select images which similarity is greater than half the maximum similarity found. We tested the LBP GIST feature and its the corresponding loop closure detection on two data sets which refer to outdoor environments. One, Malaga 6L, refers to a parking lot, and city center to an urban area. First, we analyze the modifications to winner-take-all hashing. For this, we use recall measure, which is the number, the percentage of loop closure found for a given threshold. We also use selectivity, which is the fraction of the total items in the database that we retrieve for a given threshold. In these images, instead of using selectivity, we plot 1 minus selectivity, which allows us to analyze these images as if they were precision recall curve. So the higher the value of the 1 minus selectivity, the better. We can see that the IDF modification is very effective. We have lower selectivity when we apply IDF, and the relative similarity threshold condition was helpful in this dataset, city center, but not as helpful on the Malaga dataset. Here we have mean computation times for different stages of the algorithm. LBP GIST extraction takes about 4 milliseconds. The hashing operations have mean computation time of around 2 milliseconds. And with the hashing scheme applied, LBP GIST similarity is very fast, on average 0.4 to 0.1. We can compare this to a bag of words system, which is published, where only the feature extraction stage takes about 14 milliseconds, which is much higher than the whole system that we propose. In terms of accuracy, we have also data for the bag of words system, and there is another feature close to similar to ours, brief GIST, which is also published with an accuracy of 32% for city center. When we compare these values with the LBP GIST, we see that our system performs better. there is a higher recall rate for 100% precision with our system. In conclusion, in spite of its simplicity, LBP-GIST showed accuracy gains over brief-GIST and another state-of-the-art bag-of-word system. When compared with the bag-of-word systems, this system is faster. The extraction of LBP-GIST is much faster than looking for local image features. In our system, the overall computation cost was kept lower by using a suitable hashing scheme. And the tests we carried out demonstrated the benefits of the modifications we proposed to the hashing scheme. Particularly the IDF scheme was most beneficial. Okay, that is all. Thank you.
Okay, so we have time for one or two short questions. Well, first question: in your work, you use lots of the domain is continuous, but sometimes you use and it's discretized artificially images and so on. But in your work, you use lots of thresholds that are based on basically being greater or lower, and then you transform the domain into a binary one. Do you think that it's the best approach, or what are the dangers or benefits of that approach?
So we use thresholds when applying LBP on the modified threshold function. Yes, those were tuned by hand, so there may be danger that those are not optimal in every situation. Yeah, that's something that could be exploited further to analyze how those thresholds should be adaptable to different situations. That could be the case, yes.
Yeah, the idea was more discrete versus continuous, and
the final decision about loop closure detection uses a threshold, but I mean that's I think there is no way around that, because that's a yes/no decision. At least in this case, we could, for instance, use an integration of time information, and then we could make a more informated decision. But if this is just a yes/no decision based on one image, we must compare it somehow to a threshold.
Mm-hmm. Yeah, mostly the idea was if you have a compare 0-1 or a comparison in which you have different levels, even discrete.
Okay, like a fuzzy, some kind of fuzzy transition.
Similar approaches, yeah.
Yeah, well, the main benefit of LBP is the fact that it uses binary information. That's sure. That's why it's so fast, and it's easy to convert it.
Yeah, my idea was the benefits are obvious, but the dangers are always obvious. Okay. It's more for you to discuss a little bit that.
Yeah. So of course there are other descriptors which like SIFT that computes intensity gradients and so on, which are integer numbers. Yeah, this has the benefit of being so fast, which is interesting for loop closure detection.
Okay. More questions, Antonio Paul?
The data sets you are using are outdoor data sets.
Yes.
Have you tested in indoor?
Yeah, we only for now we only published for outdoor data sets. I have tested, but we haven't published results on that yet on one indoor environment. Those are more difficult to tackle with this approach because there are more similarity between different places, and also this kind of feature is not so robust to orientation variations of the robot, and in indoors environments that will be more visible in the image because all the objects are closer to the robot, and small variations give rise to higher appearance variations. Yeah.
Okay, any more questions? No?
Because when you use only image, you can have two exactly the same, exactly identical images in two different places, and you will detect that as a loop closure.
Yeah. Well, that is true. In the similarity computation stage, there is this weight factor to the similarity measured, and in the outdoor data sets that was not an issue. I believe that in indoor environments there will be higher repetitivity in the images, and that may be an issue. The thing is, if we conclude that there are lots of image areas which are similar, they should be given a lower weight, and this will in the end up in lower similarity. So I hope that will not be such a greater issue in indoor environments. Concerning other information, we have not integrated this with odometry measurements because in the first example, in the second slide, the main conclusion is that we cannot always trust in odometry. I made some experiments and should work on that further, combining this with the depth information, but it's more or less the same thing as with the image. Just will give us a third dimension to the data.
Okay, so let's thank again Francisco for his presentation. Right, so we'll go to the second presentation. It's about a very hot topic on intelligent robotics, simultaneous localization mapping, and the title is Online SLAM based on a fast scanning matching algorithm, and it's going to be presented by Eurico Pedrosa.
Okay, now it's on. Okay, my name is Eurico Pedrosa, and I'm here to present the work entitled Online SLAM based on a fast scan matching algorithm. So I will start to present you my motivation for this work, and I will go through to explain you the scan match algorithm that that I'm going to use, and then I'll try to explain how we adjust this algorithm to use on SLAM. Then I'll finish the presentation with a few experiments and conclusion. Okay, as you can see here, in our group you have more than one type of robots. You see here 2 different robotic applications, but we try to use the same localization algorithm. This localization algorithm is called the perfect match, and it has several, let's call it skills, not skill, but properties that motivate us to use it. First, its speed. As you can see here, I compare it with the Monte Carlo localization, which is a particle filter localization algorithm. As you can see, the perfect match always goes through 0 or near 0, while the Monte Carlo localization has a little bit more of execution times. The next one is the accuracy. I don't have a ground truth, but I compare it with the path that the robot made using the Monte Carlo localization, and compare with the perfect match localization. You can see here this red path. They are very look-alike, so I guess we can use this algorithm for localization with quite accuracy when compared with the Monte Carlo localization. As we all know, localization requires a map. And as you can see here, this map is a grid map that was built using the observation of the robot. But to create a map, we also need localization. But this is kind of a chicken and egg problem. You need localization to create, you need a map to do localization, but also need localization to build your own map. This problem is called the simultaneous localization and mapping, or SLAM. So the question is, can we use the perfect match in SLAM? Let's see if it is possible. So let's put the localization problem in a probabilistic framework. What this says is that the estimate of the robot pose is given by its measurements and its motion action. That is proportional, and of course, I'm sorry, the map, that is proportional to its measurement model and its motion model. What the measurement model says is tries to calculate the probability of a measurement given a certain pose and map, and the motion model is what is the probability of a pose given its motion action and the previous position. The measurement model assumes more than one measurement. Here we do a simplification that we assume that all measurements are conditionally independent, so we can do this factorization to calculate the measurement model. The measurement model used here is the likelihood field. What is the likelihood field? We start by calculating the global position of the beam endpoint. Then we try to search what is the distance to the closest object in the map. And then to calculate this probability, you use this function, which is a function of the original perfect match. To speed up this search, we use a lookup table that is built using a Euclidean distance transform. As you can see here, we replace that distance instead of searching. Every time you have to apply the measurement model, we can do a lookup, and it's very fast to do this. This is one of the reasons why the algorithm is very fast. Now, let me try to explain you how the localization works. So what we do is we take a non-probabilistic estimation of the pose of the robot, and we try to maximize this likelihood. So to try to find, this is to say, what is the pose that maximizes the likelihood of being in that position, given the measurements and the control actions. What we really do is to calculate this problem using this maximization, using a gradient ascent in log likelihood. We use the NR-prop algorithm to do that. And another thing is that we do this in log likelihood. Why? Because it simplifies the calculation. You have here predatory, now you have a sum of all the probability of all measurements. And this likelihood can be, this is the equation to calculate the gradients, because we need the gradients to use a gradient descent algorithm or ascent algorithm. I just want to highlight this. This is, as you saw, is the Euclidean distance transform. You cannot have these gradients in closed form. So what we do is to use a Sobol operator to find the gradients in this position. Next, how can we do mapping? I think this is a typo over here. How can we do mapping with a perfect match? Well, if you remember the initial formulation, we have a static map. So if we are building a map, we can replace this static map with a function that incrementally builds a map. Given the position, the current position, and the measurements, we can incrementally build an occupancy increase. So now the problem of localization and mapping is divided into components. First, we do the localization using the map built so far, and then, of course, update the map with the newly calculated position of the robot using the most current measurements. However, this has a few problems, or it requires a little bit more of work, because, as you remember, I talked about the distance transform. The distance transform is calculated from a static map. So if the map changes, so the distance transform also has to changes. But so therefore you have to calculate this new distance transform for our algorithm to work, and must be done dynamically. The first naive solution that I've done was to, every time there is an update, I will calculate the full distance transform, and then I will apply the Sobol operator to that distance transform. Well, this works, but it adds a constant overhead of time, and I think we can do better. So for that, I'm using a dynamic Euclidean distance transform that only updates the cells that were affected by a new update of the map. As you can see here in this video, as the occupancy map is being built, we are also building a distance transform map. In the end, it only changes, small changes. So this, as the map is being built, as you can see, the time to calculate the distance transform also decrease, which is a nice thing. Another thing that we do is to use an interpolation scheme to calculate the distance. As you know, the map is discrete, and what I'm trying to do here is to put it in the continuous space. And I do this using an interpolation, use a bilinear interpolation. And for the gradients, as we know, the gradients can be calculated using difference here. So I make the difference of the x's and of the y's, and I also do an interpolation, see how much each gradient is used in that measurement. Okay, experiments and evaluation. The first thing that I did was to, of course, run the algorithm and see the outcome of that. As you can see here, we have a, oops, sorry. This is a map. This compared with the map obtained using the G mapping algorithm, which is very popular and very, let's say, state of the art. And as you can see visually, doing a visual inspection, they look very alike. So it's good for localization. So you can use it. But I think this is not enough to evaluate our approach. What I did next was to use a SLAM benchmarking tool that tries to give values of the errors, the mean average error of the SLAM solution. What it does is, instead of using global ground truth to calculate errors, which may be unfair, because imagine this map. Well, this map may not be globally consistent, but it has all the features needed to localize. You can see here it has the walls and even the doors. So it's useful for localization. But if you use global ground truth, it will give you a bigger error if you do like they propose. What they propose is to use the global displacement ground truth. So it calculates at a given time what should be the displacement of an action. So it's how it calculates the errors. I use 3 freely available data sets. The one from Access Building, another from the Intel Research Lab, and another from the Freiburg Building 79. Those was mapped already done using the algorithm. What I have here is 2 tables. The first one gives you the translational errors, and the errors are compared with other solutions, other SLAM solutions. Here, this is a SLAM solution that uses ICP, also scan matching. And here it's called scan matching, but it's ICL. It's an algorithm presented by, I think it's Andrea Sensi, which uses ICL instead of ICP. And this is the raw backwise particle filter, which basically is the G-mapping algorithm. And this is a graph mapping, which is a full SLAM solution for, it's a full SLAM solution for mapping. As we can see here, the green ones highlights the best one. So in translational errors, our solution is a little bit better than the rest one. The worst one is this one. And in rotational errors, we are 2 out of 3, but we are not the worst ever. So in terms of execution time, you can see in this graph that it takes on average 5 milliseconds plus the standard deviation, so I guess, but 10 milliseconds at most. As you can see, as the map is being built, the execution time reduces. This is due to the incremental distance transform. As the map is being built, we're only doing localization and not map building, or less map building. And another is the Intel, which you have 2 milliseconds on average, which I think is quite fast compared with maybe GMAP. It takes 1 second instead of 2 milliseconds. And another one is the last one is the Freiburg building. Also have an average 3 milliseconds of execution time for the whole map. So to conclude, I guess we can say that the perfect match can be used for SLAM. It can create consistent maps and can say that it's accurate and take into account how we do our benchmarking. And it's fast. I think it's fast. So, thank you.
Luís? Thank you for the presentation. It's very interesting your system of doing kind of a loop in terms of using a kind of a loop in terms of the localization, updating the map and then the new map being used again for localization. But my question is, in that whenever you have a loop, you may find situations that are not stable. I would like you to comment on this and see. Maybe I'm not really sure. I don't have any clue. So you may say no. We've studied it and there is no
possibility. For problems where you have big errors in motion, this solution is a little bit fragile. So a big error will result in catastrophe. It's not useful. So, for instance, I tried in the Killiam Hall. You know the Killiam Hall dataset, which is a dataset with big corridors and big loops, and with big errors in the odometry, and it fails.
What is big for you in this case?
I don't know. I would say I think bigger than this campus. the data set in terms of dimension.
No, but I mean in errors. You were saying big errors. What
The
magnitude?
errors that I cannot evaluate the errors because the map isn't consistent. It just fails. Everything in the end, everything will be free, a free space because it fails so much. I cannot create a map in that situation. So this works in situations where we have, assuming that we have lasers, you have good with small errors, right? Measurement with small errors. But the data set they provide, that kind of data set have, the odometry is not very good. And without any pre-processing, I don't do pre-processing, the errors are so big because the perfect match, when you do the localization, the optimization, the initial guess is given by the last position plus the displacement of the odometry. So the odometry gives you a hint. If the hint is too far away, the optimization is local. So we are so far away from where we should be. The locally, we fail.
I understand that. If I may, only a final comment. I understand that, but in that case, may I suggest that you try to define a threshold or
yes, that is on my to-do list. Yes,
bigger.
yes. That is what most of the other solutions, for the ICP solution, does that. If the error is too big, they just cut off the error. I tried that. No, I've tried that, but I was going to no pre-processing first. Then I will see, of course, this because it's like I said, it's a little bit fragile to big errors in odometry.
Thank you.
Any more questions? Any more questions? No? Okay, so let's thank again Eurico. So we'll go to the third presentation that continues with the team of autonomous robot navigation, here with a very interesting application. And thinking about our social programs, this is a very interesting application, 3D digital maps for vineyard autonomous robot navigation. It's going to be presented by Olga Kurant.
Good afternoon. Good afternoon. Okay. As the title suggests, this work presents or introduces a new survey methodology. For creating 3D digital map. Okay, 3D digital maps for vineyard autonomous robot navigation systems. I will first introduce the motivation to let this work. I will do the specification of the localization of the study area. After focus on the methodology details and present the results and conclusion and consideration for future work. As you can see in the image, the background image, we can find a vineyard with certain characteristics that are typical from the market region. As for motivation for this work is the non-existence of an accurate digital elevation map of the studied region, the possibility to create a geographic information system project with information of the vineyard particularities that could be used for precision agriculture, the validation of use of a special GPS, a differential GPS in the region that can has integrated a GMS modem and have corrections in real time with three-dimensional centimeter positional accuracy. And finally, the development of a methodology that can be used as an important tool for path planning for identification decision-making points. The study area is located in the northeast of Portugal, in the municipality of São João da Pesqueira, Parish Everdosa do Douro, in the property of Bateiras. Describing the methodology is a part of a procedure chart. The procedure has three inputs. The digital elevation map produced by the Portuguese Military Geographic Institute, produced it in 1966. An image for acquired, a satellite image for acquired for Google Earth image, and data points acquired or surveyed by this methodology collection of this information. As output, an accurate digital elevation map with accuracy to be used in for navigation purpose. The methodology consists on three steps. The first one is the study area location and characterization. The preparatory work for field data collection and GPS field data collection. In the first stage, stage is the visit to the vineyard with some equipment, a simple equipment to evaluate the particularities of the vineyard. It was chosen a parcel of the total vineyard. This parcel has a long terrace that contours the forming wavy curves, is a condition for selecting this area. There is short terrace known as dead-end terrace in contrast to the others, due to two kinds of discontinuities, natural and artificial ones. And as also different vineyard paths. As you can see in the picture, the kind of natural discontinuities can be caused by, in the image, a cliff, or by rainfalls that can destroy the vineyard terraces, due to the need to the vineyard to contour the hill, and due to artificial discontinuities that the terraces are short. In the picture we can see the system created by the man to collect the water in the rain, and the post of electricity. Different paths in the vineyard. One where the car can move, and another where only a tractor can circulate. This is the first step of the methodology. The second step is to prepare the information for collecting data. It's important to modeling the vineyard peculiarities, the definition of a strategy to collect the data, defining the form to collecting data, defining as well a structure to collect the information acquired from the vineyard, and the configuration of the GPS, DGPS, and the software associated. In the modeling of the vineyard particularities, we define three kind of surfaces. We identify, label and identify terraces with slightly accentuated slopes, passes with a great enhanced slope, and the transition. We have defined 5 forms of transition, surfaces of uneven configuration that we can view in the figure. The definition of the collecting strategy, or the strategy for collecting the data. We have defined 2 criteria. The first one, the acquisition is based on a variable spacing surveying according to the characteristics of the terrain. In the places like terraces and passes where we find a small elevation, it is then the survey with sample constant sample points. In places like transition, we do the surveying with every break line, in every break line with more points. For quality control of the creation of the digital elevation map, they are surveying a group of points that will not be used to create the digital model elevation. We create a surface model and use the points surveyed in places where the robot can move to verify the different elevation obtained. As finally, we surveyed the center lines for every possible navigation trajectories. The definition, the base data structure as attributes with some characteristics, like the coordinates of the surveyed points, and some characteristics, the type of area as output, and no data points that is served in path or terrace, and the number of typed area. Another characteristic, important characteristics we have put in the database is the vine. When the surveyed point has a vine, planted vine, the value is yes, otherwise the number is the value is none. Before acquiring the data, is important to configure the equipment. The equipment was the GPS was configured for a positional accuracy better than 2 centimeters, using a filter mask for collecting the data. And after we go to the vineyard and collect the data. The mode for collecting the data was top-down scanning during all through all transition in all terrace, and late and finally the path that surround the vineyard. As a result, we have then a series of maps for creating a triangular irregular network that is the model, the digital elevation model, and we have analyzed the results. In this map, in this figure, you can view the collected points and center lines obtained, and we verified that they are well defined. The outer and the inner edge of the terrace are surrounding the center lines. After the analysis of this information, we created the digital elevation model, utilizing area that limits the vineyard, and we can view the orthogonal projection detail. We can view in the figure that the vineyard is represented well. Is well represented. Is the definition? We can compare the definition obtained, analyzing the results. The digital elevation map and profile created over 10 meters contours the information of the Geographic Institute, and you can detect a gap of 20 meters between the lowest and the high terrace, and with information acquired from the GPS with the accuracy over control lines of the 10 centimeters, we can verify that is visible the different height between terrace in first of nearby 2 meters. We can see the 8 terrace in the profile. As a result, it is proved that the use of this kind of GPS can be used to assist the navigation in this kind of vineyard. It was developed a methodology that could be used as an important tool for path planning, for identifying decision-making points, because the configuration and of the transition areas, they are defined well. And in conclusion, we can say that the methodology can be defined as fast, rather inexpensive, and involve a few resources. The model created by the methodology has an accuracy of 10 centimeters, sufficient detail for navigation purpose. The methodology is adequate for describe the market region VNR irregularities. As future work is important for creating a simulation environment of the vineyard and test the navigation strategy in planning platform, and the improvement of the database with information of possible maneuvers and tractor can perform. Thank you for your attention.
So we'll have time for some questions. Questions? Okay. First question. One of the problems on this kind of environments is that we are not using regular robots with capabilities for maneuvering, and basically the kind of things that will maneuver in the environment are cars, tractors, and other things. How to go from regular robots maneuvering in the environment to cars, tractors, and other kinds of non-robots that will maneuver really in the environment. Yeah, sure.
What is the kind of autonomous robot to put in the vineyard?
No, more or less. In the vineyard, you don't have the kind of autonomous robots that you typically have. Wheeled robots or the normal kind of robots. You'll have tractors, for example. The idea is the difference between describing the robot for regular robots and for enabling tractors for maneuvering in the environment.
Do you know my opinion?
Yeah.
Okay. And my opinion is that it is necessary for this kind of vineyard to use not a robot, but a tractor and instrument the tractor, because the crop activities are special.
Yeah.
And the robot can fall down and damage himself and the vineyard. That it's important to use a farm tractor, I think.
Mm-hmm. Yeah.
I answered your question?
Yeah, more or less the idea was how, because the approach is focused on mapping for normal robots,
Okay.
compared with, we will not have normal robots on the vineyard. You'll have tractors or tractor robots.
Yes, I think it's okay. In my opinion, to be efficient and use the equipment that agriculture has in the actually in the vineyard to do these tasks, is important to maintain the equipment and make the instrumentation for this kind. The map is important because
So, questions, Antonio Paulo?
In your experiments, normally, how many points do you have in a typical map?
Okay, I have two kinds of information. Points acquired, surveyed meter and meter, like individual acquisition, and for central lines. the acquisition was done with a certain time, because the equipment was put on a tractor, and the tractor was travel on doing the activities in the vineyard, and the equipment collect the GPS points second for second. Okay, the resolution is, the number of points is is greater in a path where where a tractor moves to collect the data manually is very hard to do. This work.
Okay. And do you think to collect data with a semi-autonomous robot is a possibility?
Yes, I think so. Yes.
Okay.
It's important to do this. But the robot, we have to put the equipment in the specific orientation, because in this location to collect the edges is difficult. The edges of the terrace is difficult to put, and the signal is not every time accurate. We have to use a store station in a certain location to obtain this accuracy.
Okay. And do you think that in the future you can use a higher level of representation of the map using these points to don't have so many data to process in real time when it will be used by a robot in real time? Maybe the map will be simplified, creating maybe a topological map with the paths only. Layer.
For that, you need some topological information also. You need to know that that's terrace number 3, for example, or yeah, sure.
Database, in the database, structured database that we have defined, the number of each path and terrace and the specificity of each transition is perfectly defined.
Okay.
For navigation purposes, we can compare the configuration of one transition to the position on the map.
Yes, it's just to announce that you have more information than a simple grid map.
Yes.
Yes. Okay.
Yeah. Okay, so time for the last short question. If someone wants? No? Okay, so let's thank again Olga. We'll continue with the same subject of this session, autonomous navigation and mapping, and now going to more work about topological maps, and it's going to be presented by Philippe Sands and is entitled Towards Extraction of Topological Maps from 2D and 3D occupation grid maps.
Okay. Hello, my name is Filipe Santos. I'm a researcher at Inestec. I will present a part of my work of PhD. My PhD work tries to include the human into the process of mapping and localization process of the robots. The motivation behind of this is that the robots that we have nowadays, they are in high factories and they can only perform a limited set of tasks. And these tasks are pre-programmed by the programmers, skilled programmers. These robots cannot understand and do not interact with humans. So if we want to put these robots or these robots in our homes, in our offices, or in public spaces, these robots should be capable to understand sentence and acquire information from that sentence. For example, if I say to my robot, "You, robot, please go pick my pen that is over the table in my office," this robot should be able to include that information in that map, in the map or the knowledge that he stores in his memory. Nowadays, these robots that are in these high-tech factories or that are in our research laboratories use some kind of SLAM approach that was spoken before here in a later presentation. This kind of approach creates a kind of occupation grid map of the environment, but this kind of maps is useful to help you or to help the robot to create a map of the environment and to localize. But this information that he acquires do not have any kind of human information, do not link the space to human words. For example, if you ask to one of these robots, "Robot, where are you?" he will tell you a number, but this number don't have any special meaning for you. So this is the question: how we can increment these maps that is stored by the robot in a SLAM approach and include some kind of semantic information and link human words to that knowledge acquired by the robot. There are several approaches. The first person that deal with the problem, that was Frank Delaert. In 2004, it says that the SLAM should be extended to some cognitive level. He wants to say that this occupation grid maps that are obtained in the SLAM should be abstracted to higher levels. Galindo in 2005 had proposed this architecture where it divides in several layers or abstracts the occupation grid map in several layers. For example, after the occupation layer, it includes a symbolical level where it segments the space and attributes some kind of human words or link to some significant or abstract words and creates a relation between words and the segmented space. Afterwards, Hendrik Zender optimized this framework and creates a more clear approach to this problem. And he divides the problem in the sensory level layer and the place layer, where he describes the places, and the conceptual layer, where is extracted from the acquired information the shape of places, objects, and that kind of information that is related to a conceptual map. Okay, looking to that work, I think that this should be improved, and we have suggested another framework where we include the object in the layers after the place, after the description layer of the place. What I mean, instead we have an occupation grid map that is obtained via a common slum, and then we have another layer where is described as the places, where we have a topological map. Then, connected to this topological map, we have an object map that is connected to the topological map. At your left, you can see how this works. At the topological layer, our occupation grid map is abstracted and segmented in places. For example, a place can be segmented, in this case, in 3 places. And these places are, to this place, are related objects, or connected, or placed objects in that places. For example, there, I'm using attributed graphs. I mean with this, for example, the topological map is a graph where each vertex is augmented with some attributes. For example, the shape of the place, the visual signatures, and other kinds of features, but in the higher level. On top of the topological map, I have an object map where I can define my objects that are related to a dictionary of objects. These objects can inherit some characteristics to each object. This is the kind of representation of our framework. Let's look in detail to the topological map. Our topological map is composed by is a graph that is composed by a set of vertices and by a set of edges. These vertices are augmented with human words, walls, which are defined in a space defined by the occupation grid maps, real and virtual walls, and is augmented also with visual signatures, which can be some kind of gist or some that are or color histograms that are assigned to each place with a unique feature, as a unique features. The edges are also associated to real or virtual doors. These virtual or real doors can have also some human word attached to him. Then there is also the definition of the door, if his size, if he's open or not open. I will not enter in details because it's not the main purpose that I want to show. It's not my intention to detail a lot about that, but this can be useful if you have 2 robots working and cooperating one with each other, and you can tell that one door is closed and another is open, and this can help the robot decide what is the best strategy to reach from one place to other place. So this topological map is managed by a layer where I have several components. For example, here I can explain a little. For example, the topo parser is a component that receives some sentence that are structured by an upper layer, that is a human interaction layer, that structures the sentence in accordance to the definition that component, and that component can translate that to a topological layer, to another topological map that can be in the future merged with a topological map that is inside of the robot. For example, if I say to the robot, you are in the corridor, and your left you have room A, and your right you have room B and room C, this sentence is translated to another graph, which will be merged with the graph that is inside of the robot. Then, this is done by the topo-merge component. Then we have a placeman, that is another component that detects if the word that is attached to the spatial vertex or to that node, if that is the right word that is associated to the place. Imagine that robot reaches to a place and he have a word attached to that node or to that place, and you don't have the sure about that name, you can ask to the human. Or if you don't have any name attached to that vertex, it can ask to the human what is the name that is attached to that place. Then we have the topo visual signatures that what she does, this component is acquires information from the environment and gives to each place some unique feature. Then we have a topo state. This is a simple component which says to the robot or to the upper layers in which state he is in the topological map. We have then the GR2. This is the component that I will speak now, that I will talk about now. That is a component that the problem that he had is I have a grid map, and now how I do pass this grid map to a topological map. How I can segment this this occupation grid map in a topological map. So this is the problem that I will speak now. How can this be done? This is the figure that represents the problem. Here you have a human looking to the occupation grid map and abstracting this grid map into a topological map, okay? I want to know how the robot can replicate this task. So let's talk about the problem. In the literature, we have a lot of works trying to extract the topological map from occupation grid map. However, this is done, or the most work that is done here is to solve the problem of path planning and navigation planning, and the problems related to navigation. And most of them over-segmentation or sub-segments these occupation grid maps. Do not do the similar work as a human. And most of them works in 2D grid maps. And we have in some robots, especially in our lab, we have robots that makes a 3D map. And how can we extract from this 3D map this topological map? We don't have found in the literature some approach for this. Another problem is this approach do not extract the doors and the walls that can be extracted a priori from these occupation grid maps. However, there are several concepts that we can extract from this state of the art, namely the Voronoi maps that are widely used by Sebastian Thrum and door detections that is used by Joe. Sorry. Okay, how we define our approach? To extract these topological maps from this occupation grid map, we have divided the problem in 5 stages. The first stage compresses the occupation grid maps in a 2D maps. Imagine that in the figure of our problem, we have a 3D map of the first layer level of our university. How we can extract this, I will talk about this later. Then I will, this approach detects doors, tries from the occupation grid maps to find where is the most likely place for a door existence. Then it extracts the Voronoi graph from that map. Then it constructs the topological maps with door and validating the doors. Then he optimizes the spaces and augments this topological map with real and virtual walls. how we compress a 3D map into 2D. This is a simple process. We pick layers, for imagine, defined by the level from 0 meters to 2 meters, and we compress that in a 2D map. This is followed by that rule. Is occupied if the number of occupied cells is above the number predefined as a perimeter, and the number of free cells are lower than the max cells. This is done in the vertical perspective, the perspective of cells, and this one if the number of free cells are upper of a number superior to a number of free occupied cells. 0.5 is if is unknown. Yeah, otherwise, I mean. Then how we detect the doors? The concept is very simple. We have predefined the door. We know that the door is have something a length. For example, imagine that the door is predefined that have 9 centimeters to 10 centimeters. This is my door. So we first construct the map of distance of our topological maps, and where there exists a place with a distance to the closest occupied cells with the value inferior to the predefined size of the door, that can be a door. And then you will try other condition. You will try to find if there is a passage from one side to other side with an higher space. I mean, a door, if you imagine this as a 3D, imagine this as a 3D plot, you will look that the door is placed in a critical point, is the local minimum in the top of the maximums. This, okay, is this. It tries to find, it finds the critical points that are imagine a wheel, a climbing wheel, where you have a lower maximum, but in the sides you have upper wheel. But this is defined by that equation. Then we extract the Voronoi graph. What is a Voronoi graph? Voronoi graph is a kind of a Voronoi graph is composed by a set of edges. These edges are defined by in the map of distance by the cells that have at least 2 occupied cells at the same distance. And there is a Voronoi graph extracted from the occupation grid map that is based in that work from a student from Wolfgang Bogard. I have improved some things there because the edges have appeared a lot because the segmentation, because the discretization of the map, and I have improved some works, but in the paper is described what was improved. Now, what we find, what we do. We create the topological map doing this process, find the local maximums inside of the distance map. In that distance map, we have a value. That value is assigned to each maximum. This gives a circle. To each circle, we do not accept another circle that intercepts that circle, and we only left there that ones that are the biggest one. Because if you imagine the distance map, we will have a hill with a lot of hill and a lot of local maximums. So this is the final result. And then we find the connections using the Voronoi maps and the edge of the Voronoi maps to define the connections between the places. Then what we do? We have circles that define each place. This place, these circles are inflated. Imagine a balloon that is filled with air. So we inflate these circles to the maximum, to the farthest occupied cell, using the following rule. We divided this circle in 8 points. These 8 points are inflated to the farthest cell, occupied cell. This inflation that is appear here is controlled to allow us to see the delimitation of the place. But and then we extract from here the real doors, the real walls and the virtual walls. What defines a real and a virtual walls? A virtual wall is a wall that don't have any occupied cell. A real wall is a wall that is over over the occupied cells, and over the occupied cells. If you imagine the edge of one this inflated octagonal delimitation place, if that falls inside on the top of occupied cells, this is our real wall. Okay, this is a summary of our topological extraction. We compress the 3D map in a 2D map, and then we create a map of distance. This map of distance is used to estimate where is the most likely place to exist for a door existence. Then we extract the Voronoi graph. Then we extract the topological map, and then we extract the real and virtual doors and walls. I will show some results. This is the result from our the segmentation of our laboratory. The results is shown there. This is with another virtual scenario that was implemented in a virtual scenario, and we have extracted these walls. The walls are represented by blue lines and the circle red. And in your left, in the upper figure, you can see the nodes are represented by red circles. The connections are represented by black lines, and the places where a door can exist are represented by cyan circles. In the bottom figure, you can see the segmentation of the place. This is another scenario that is with the TrackLabs facility. This was found in the web, and we have applied our approach. We have compared this segmentation to a human segmentation, and we have found that the segmentation is over-segmentation. The algorithm detects more places than the humans, but is not so very different, and we want that. We don't want that sub-segmentation, because when the human wants to describe to the robot how the place is, if we have less nodes and we try to merge that to graphs, we have problems. It's more easier to us to merge one node to two other nodes than to merge one node and split a node that does not that includes two places. The results are similar. Afterwards, I have tested this in another scenario with well-known occupation grid map obtained using the DP SLAM. And here you can see on the top the original map. The left, in the top, we have troubles detecting the doors because they are not so usual, do not have the common size. In the bottom figure, you have the topological map extracted using in the appeared form that is extracted from the topological with the circles, and then we have the inflated where we extract the real and virtual doors. This is another case, and that works well also. You can see the segmentation, how he considers the places. Okay. We have used this in the large in the work using the ISLAM framework, and this gear to allow us to extract the topological map that was used after to merge to the human description. In this case, there was a human describing the place as follow. In your robot, you are in the corridor. At your left, you have room. I will say A, room B, and your right, room B, and afterwards you have room C. Afterwards, you have room D, and in your front, you have a corridor or something like that, a corridor B. As future work, this inflation is not the best approach, because we have used 8 points to describe the place. Probably we should use something closer to us splines, and also should be considered that can exist some noise in this occupation grid maps, and we should remove or see how can be improved, or how can define the best way what is the wall. The door detection should be also improved, but this should be used also in conjunction with some imaging detection, and also when there is noise or something that in the occupation grid map, you should use this to extract some kind of places where other algorithms that works in the ISLAM should look for objects. Okay, is that?
Okay, so we have now time for some questions. One?
Of the robots, and how it identifies tables, chairs, even computers or pens or whatever. But you didn't develop for the rest of your presentation, so your robot wasn't actually able to identify those objects, or were it?
No. I have started defining what should be the framework, how this should grow up. Okay. I defined the object dictionary in my layer because I consider that is important, because this dictionary should describe the objects closer to the sensors that are used in the robot. So this will depend on what kind of sensors we have used in the robots. The upper layers related to object detection, I haven't explored yet. I have defined it, but I haven't explored, because the topological map and visual extraction of feature, merging the description given by a human with the topological map is a complex task. So I haven't explored.
So I got another question. What do you think is the best application for this kind of robots? Is it mapping places we don't know, or just using them for navigating in places that we already know?
They can work in a place that they don't know, because this is iterative constructs his knowledge. First, he constructs the occupation grid maps, and then he tries extract an abstraction of that geometric information and try to connect that abstraction to human words. This is useful because if the robots do not know to relate words to objects that are present in the environment, you cannot do what you want. So
I'm thinking more, for example, for espionage applications.
Oh, okay.
Thank you
Okay.
for your availability.
All right, more questions?
Hi. First, I would like to congratulate you on the work, because I think with the advent of service robots, this will be something essential for robots. My question is, in the maps that you had of your lab, we could say almost that those maps were very clean,
Yeah.
while our robots live in a cluttered world. And in the latest maps that you showed of the Intel labs,
Yes.
where you have other structures in the environment, you have a lot more candidates. What I would like to, well, my intuition tells me that probably those candidates come from the use of the Voronoi algorithm. Do you think it is the best method to try to detect these kind of rooms, or the structure of the buildings, or maybe we could try, I don't know, maybe clustering algorithms over free space or something like that?
Yes, that clustering is done by Pronobis. That is a work that is related to Hendrik Zender. But I have forgotten during my presentation tell that this compression from a 3D map to a 2D map removes from furniture, for example, from your map. If you look there, in the first map, the occupation grid map is more cleaner than the second one. Why? Because this is a property that this compression does. That is, when you compress the map, we will remove the objects, so it will be more cleaner. If this is the correct approach, or is the most adequate approach to do the work, I think yes, because I consider that the topological map is to describe the places with a set of places, and if in the case of the Intel lab, he over segmentates, so segmentates the place. But if the human describes the place to the robot with the graph matching, I can join graphs and create and join places and get the best, not the best, but a closer description of the place.
And concerning the work of Pronobis and novelty detection, tomorrow we'll have a talk about novelty search, probably with some interesting ideas, although not exactly on the same subject, maybe quite interesting for answering that question. The plenary talk tomorrow morning. All right, we can have still some more questions. Just a last short question. No?
In that map, your approach got two circles in the large room in the upper part of the map.
Yeah.
Do you have any kind of merging methodology?
Yes. For example, I have a not so during the presentation, but for example, for the corridors, this will over segmentate the corridors. I have approach that detects that the circles that are collinear and do not have a door between them. When this happens, he merges, or he tells to the algorithm that there are collinear circles, and probably that is a corridor. That are the circles represented by blue circles. In the in the other room, there are two circles defining a place. Yes, but they are afterwards merged. Why? Because when the human have described the place, it describes that there is one room at his left. So the robot, with the graph matching techniques, he can merge that two graphs and know that is one place only. Okay.
Thank you.
Okay, so before finishing the session, and again thanking Philippe, iRobot will continue in the afternoon after the coffee break with a session mostly about sensing and perception, and then tomorrow we'll have two sessions, one in the morning basically concerning control and planning, and then in the afternoon concerning learning in robotics. So again, let's thank Philippe for the last presentation and all the speakers. We'll continue the coffee break on the other room.